Welcome to the Deep Dive, where we cut through the noise and get you straight to the really fascinating nuggets of knowledge. Today we're diving into something pretty fundamental, something that touches your life every single day, often without you even realizing it. We're talking about heat exchangers.
That's right. Think about, your home's air conditioning or maybe the radiator in your car. Even something simple like how your thermos keeps coffee warm. These are all fundamentally heat exchangers. They're really critical pieces of engineering.
Exactly. And at their heart, they're actually quite clever devices. They're designed to move heat from one fluid like air or water to another. But here's the really crucial part. They do it without letting those fluids actually mix together. It's quite an elegant solution, really, for transferring energy.
It really is.
So our mission today is to sort of unpack the surprising facts about these components. We'll look at the basic types, how engineers figure out which one to use, how they analyze them, and maybe the most surprising part, how they even operate inside your own body. We're here to give you that shortcut to being genuinely well-informed on this.
Sounds good. It's a surprisingly deep topic.
Okay, so let's start unpacking this. When you first look into heat exchangers, you quickly realize, wow, there's a whole family of them. Each one is like meticulously designed for a very specific job. And they pop up everywhere, right? Household heating, cooling, massive industrial plants.
Absolutely. Power production, chemical processing, you name it.
The simplest place to maybe start understanding them is with what's called a double pipe heat exchanger. It sounds like what it is, right?
Yeah.
Pretty straightforward. Two pipes, one nestled inside the other.
Yeah, one fluid flows through that inner pipe and the other flows through the space between the inner and outer pipes. Simple concept.
But even with that super basic setup, you immediately hit a really vital design choice.
Right. How do the fluids actually flow relative to each other? That's key. You've got parallel flow, where both fluids enter at the same end, move along together in the same direction.
Right.
And then you have counterflow. They enter at opposite ends and flow, well, in opposite directions past each other.
And that distinction matters.
Oh, absolutely critical. We'll probably get into why later, but counterflow designs are just inherently more efficient at transferring heat. It makes a big difference.
Interesting. So from these simple pipes, engineers often think, okay, how can we cram more heat transfer into less space?
Exactly. Space and weight are often huge constraints.
And that brings us to what are called compact heat exchangers. These things are like masters of squeezing a huge amount of heat transfer surface area into a really tiny volume.
Yeah, engineers had a term for this. Area density. It's basically the surface area per unit volume.
Okay, so a higher number means more compact.
Precisely. And compact heat exchangers, by definition, have an area density greater than 700 square meters per cubic meter. That's a lot of surface packed in.
Wow. And here's where it gets really interesting, right? Your car radiator, for example, has an area density around 1,000.
It does. It's a great example. And what's really fascinating, connecting this maybe to the bigger picture, the human lung.
The lung.
Yeah, it's also an incredibly compact heat exchanger. Its area density is, well, it's estimated around 20,000 square meters per cubic meter. Just phenomenal natural engineering.
That's incredible. So these are used when weight and volume are really strict limitations.
Exactly. Think aerospace, automotive. And often, these compact designs use lots of thin fins.
Like you see on the outside an air conditioner unit or that car radiator.
Right. Especially on the air side, because gases generally don't transfer heat as well as liquids. Their convection coefficients are lower, so those fins drastically increase the surface area the air touches, helping to overcome that lower efficiency.
Gotcha. And speaking of compact, there's a really cutting-edge type called the printed circuit heat exchanger, or PCHE.
Ah, yes, the PCHEs. Very advanced.
The name comes from how they're made, right?
Yeah.
It's quite unique.
It is. They take flat metal plates and chemically etch tiny, intricate flow channels into them, almost like, well, like making a circuit board.
Okay.
Then they stack these etched plates and bond them together using a process called diffusion bonding. This uses high temperature and pressure, but below the melting point, to fuse the metal atoms across the layers. Creates an incredibly strong, solid block with these tiny channels running through it.
And get this, they end up being something like 4 to 6 times smaller and lighter than conventional heat exchangers doing the same job.
Which is amazing. But, this raises an important question. What are the trade-offs? Nothing's perfect in engineering.
Right. So what's the catch?
Well, despite those advantages, they tend to have a very high pressure drop. It takes more energy to push the fluid through those tiny channels.
Okay, so higher pumping costs.
Exactly. And they also demand exceptionally clean fluids Because those channels are so fine, often less than a millimeter wide, they can get blocked easily if the fluid isn't super clean.
Makes sense. But the upside is extreme operating conditions.
Huge upside. They can handle anything from cryogenic temperatures like minus 250 Celsius up to maybe 900 degrees Celsius, and pressures up to 500 bar, which is immense.
Wow. Okay. And you also mentioned cross-flow configurations earlier.
Right, that's another common setup, especially in compact exchangers. The fluids move perpendicular to each other, like crossing paths, and you can further classify that as unmixed or mixed, depending on whether the fluid is free to move sideways as it flows across. Your car radiator, for instance, usually has both the air and the coolant flowing in distinct paths, so they're both unmixed.
Okay. That makes sense. So while these compact designs are great for tight spaces,
Yeah.
most of the world's heavy lifting and heat transfer happens on a bigger scale, right?
Yeah.
With the industrial workhorses.
Absolutely. And the king here is probably the shell and tube heat exchanger. It's the most common type you'll find in large industrial plants, refineries, power stations.
Okay, shell and tube. So what does that look like?
Imagine a large outer cylinder. That's the shell. Inside, you pack a bundle of tubes, sometimes hundreds of them. One fluid flows inside all those tubes, and the other fluid flows through the shell, bathing the outside of the tubes.
And I've heard about baffles in these.
Yes, exactly. They often put plates or baffles inside the shell. These force the shell side fluid to flow back and forth across the tube bundle rather than just straight along.
So that increases the heat transfer.
It does, significantly. It creates more turbulence and ensures better contact. The baffles also help support the tubes and keep them spaced properly.
But you wouldn't put one of these in your car.
Definitely not. They're generally too big and heavy for automotive or aircraft applications. That's where the compact designs shine.
Right. What other industrial types are common?
Well, there are plate and frame heat exchangers. These have become really popular. They consist of a stack of thin, corrugated metal plates clamped together in a frame.
Corrugated, like wavy.
Yeah, the corrugations create flow passages between the plates and also add strength. Hot and cold fluids flow in alternate passages, so a cold stream might be flowing between plate 1 and 2, then a hot stream between plate 2 and 3, cold between 3 and 4, and so on.
So each cold stream is essentially sandwiched by two hot streams or vice versa.
Exactly. Which makes for very effective heat transfer. And a great advantage is they're expandable, need more capacity, just add more plates to the stack.
That's clever. Any other major types?
One more distinct category is regenerative heat exchangers. These are a bit different because the hot and cold fluids pass alternately through the same flow area.
The same area. How does that work?
Often, there's some kind of matrix material like a porous ceramic or metal mesh. First, the hot fluid flows through, heating up the matrix. Then you switch the flow, and the cold fluid passes through, picking up that stored heat from the matrix. It can be static, like that mesh, or dynamic, like a rotating wheel.
Okay, interesting. And sometimes they're just named for their job, right?
Yeah, that happens too. You'll hear about condensers, where a vapor turns into a liquid, like in a power plant or air conditioner, or boilers, where a liquid turns into vapor, or even the space radiators, which are designed specifically to radiate waste heat out into space.
Okay, quite the variety. So with all these different types, how do engineers actually measure and quantify their performance? It can't just be hotter or colder.
No, definitely not. It's about rates and efficiencies. And the key concept here is something called the overall heat transfer coefficient, usually represented by the letter U.
U. Okay, what does that tell us?
It's basically a single convenient number that bundles together all the different ways heat moves from the hot fluid to the cold fluid. It accounts for how easily heat gets from the hot fluid to the wall separating them, that's convection, how well heat conducts through that wall material, and then how easily it gets from the wall into the cold fluid, convection again.
So it wraps up all those steps into one value.
Exactly. And the broader implication here, something really important in design, is that this overall U value is often dominated by the slowest step in that chain. Usually that's the fluid with the smaller convection coefficient, the one that's worse at transferring heat to or from the surface. That creates a bottleneck.
Okay. Like you mentioned, with gases needing fins.
Precisely. Gases typically have much lower convection coefficients than liquids. So if you have a gas on one side and a liquid on the other, the gas side is often the limiting factor for the overall heat transfer. That's why you add fins there to increase the surface area and compensate.
Makes sense. And these U values, they vary a lot.
Dramatically. For a simple gas-to-gas heat exchanger, U might be really low, maybe around 10 watts per square meter per Kelvin. But for something involving phase change, like a condenser where steam is turning into water, the U value can be enormous, maybe 10,000 or even higher, thousands of times more effective per unit area.
Wow, okay. But even if you design it perfectly with a great U value, things can go wrong over time, right? You mentioned fouling.
Yes, fouling. The silent threat, you could call it.
Sounds ominous.
Well, it can be a real headache for engineers. The broader implication here is that fouling is basically the accumulation of unwanted deposits on the heat transfer surfaces.
Like what kind of deposits?
It could be anything, really. Mineral deposits precipitating out of water, like the lime scale you see in a kettle or shower head. It could be chemical reaction products, corrosion, rust, even biological growth, like algae or slime, if the fluid and temperature conditions are right.
And this buildup, it just adds a layer of gunk.
Essentially, yes. And that layer acts as an extra thermal resistance. It makes it harder for heat to get through the wall.
So it lowers the overall heat transfer, decreases that U value we just talked about.
Exactly. It reduces the heat exchanger's performance. Over time, an exchanger that was perfectly sized might not be able to meet the required heat duty anymore because of fouling. This might mean you need to design the heat exchanger larger and therefore more expensive from the start just to account for the expected fouling over its lifetime.
Does it depend on operating conditions?
It does. Generally, fouling tends to increase with higher operating temperatures and, interestingly, often with lower fluid velocities. Slower flow can allow particles to settle out more easily.
Huh. And is it a significant effect? Like, how much resistance does it add?
It can be quite significant. Just to give you a tangible idea, a typical fouling factor used in design calculations might represent the thermal resistance equivalent to adding a layer of limestone about 0.2 millimeters thick. Seems tiny, but it can make a noticeable difference in performance.
Right. Okay, so engineers have to account for that. Now, when they're actually analyzing these things, either designing new ones or checking existing ones, what tools do they use?
There are two main methods, really, depending on what you know and what you need to find out. It's like having different tools in your toolbox.
Okay, what's the first one?
The first is called the log mean temperature difference method, or LMTD for short.
LMTD. Okay, when would you use that?
This is primarily your go-to method when you know the inlet and outlet temperatures of both the hot and cold fluids. And your main goal is to figure out how big the heat exchanger needs to be specifically, what heat transfer surface area A's is required to achieve that temperature change.
So, known temperatures, find the size.
Yeah.
Why log mean? Why not just average the temperature difference at the inlet and outlet?
Good question. You can't just use a simple arithmetic average because the temperature difference between the hot and cold fluids usually changes along the length of the heat exchanger, and it doesn't change in a straight line, it changes logarithmically. If you used a simple average, especially if the temperature differences at the two ends are very different, say more than 40% different, you'd overestimate the average temperature difference and therefore underestimate the required size. The LMTD gives you the correct, effective, average temperature difference for heat transfer calculation.
Got it. And this relates back to the counterflow versus parallel flow thing.
It does, directly. Which leads us to consider again, why counterflow? For any given set of inlet and outlet temperatures you want to achieve, the LMTD for a counterflow arrangement is always greater than the LMTD for a parallel flow arrangement.
Always greater.
Always. And since the heat transfer rate is proportional to the LMTD, a larger LMTD means you need less surface area A's to transfer the same amount of heat.
So counterflow lets you build a smaller, probably cheaper heat exchanger for the same job.
Exactly. That's a huge driver for why counterflow is preferred whenever practical.
What about those more complex types, like shell and tube with multiple passes or cross-flow? Does LMTD still work?
It does, but with a modification. For those more complex geometries, the simple counterflow LMTD calculation isn't quite right anymore. So engineers use something called a correction factor, usually denoted by F.
F factor.
Okay. You calculate the LMTD as if it were a simple counterflow exchanger with the same end temperatures, and then you multiply it by this correction factor F, which is always less than or equal to 1. F depends on the specific geometry and the temperatures. There are charts and formulas for finding F.
Okay, so the LMTD method is great if you know all the temperatures and need the size. What if the situation is reversed? What if you have a specific heat exchanger? You know its size and type, and you know the inlet conditions. But you want to predict how much heat it will actually transfer, or what the outlet temperatures will be.
Right. That's a very common scenario, too. Maybe you're assessing an existing unit, or considering using an off-the-shelf model. In that case, the LMTD method gets really awkward.
Why awkward?
Because you don't know the outlet temperatures, which you need to calculate the LMTD in the first place. You'd have to guess the outlet temperatures, calculate LMTD, calculate the heat transfer, see if it matches the energy balance for the fluids, then guess again. It becomes a tedious, iterative process.
Sounds painful.
It can be. So for this situation, engineers developed a different approach. The Effectiveness-NTU method.
Effectiveness-NTU. Okay, sounds promising. How does it work?
It avoids that iteration. It focuses on the effectiveness of the heat exchanger, which is given the symbol epsilon.
Effectiveness. What does that mean specifically?
Effectiveness is defined as the ratio of the actual rate of heat transfer achieved by the exchanger to the maximum possible rate of heat transfer that could theoretically occur.
Maximum possible. How do you determine that?
What's fascinating here is that the maximum possible heat transfer is limited by the laws of thermodynamics. It occurs if you had an infinitely large heat exchanger. In that hypothetical case, one of the fluids would undergo the maximum possible temperature change, which is the difference between the hot fluid inlet temperature and the cold fluid inlet temperature, TMEM.
Okay, but which fluid reaches that maximum change?
It's the fluid with the smaller heat capacity rate. Heat capacity rate C, the mass flow rate times the specific heat, m.Cp. Think of it as the rate at which the fluid can carry thermal energy.
Smaller heat capacity rate. Why that one?
Because that fluid is the bottleneck. It requires less energy to change its temperature, so it will be the one to reach the maximum possible temperature change first. For example, if the hot fluid has the smaller C, it could theoretically cool all the way down to the cold fluid's inlet temperature. But the cold fluid, with its larger C, wouldn't necessarily heat up all the way to the hot fluid's inlet temperature. The smaller C dictates the maximum possible heat transfer. We call this Semin.
Okay. Semin is the limiting factor. So effectiveness is actual heat transfer divided by Semin.
Exactly. And the beauty is that this effectiveness turns out to depend only on two dimensionless parameters.
Dimensionless, okay. Makes it general. What are they?
The first is the number of transfer units, or NTU. NTU is defined as U times as divided by Sim. NTU is U as Semin. It's basically a measure of the heat exchanger's size or heat transfer capability relative to the limiting fluid's capacity rate.
Okay, NTU represents size. What's the second parameter?
The second is the capacity ratio, usually denoted by C. It's simply the ratio of the smaller heat capacity rate to the larger one, C equally Cmin Cmax. It tells you about the relative thermal capacities of the two streams.
So effectiveness depends only on NTU and the capacity ratio, C.
That's right. And importantly, the relationship between A, NTU, and C depends on the type of heat exchanger: parallel flow, counterflow, shell and tube, crossflow, etc.
Yeah.
Engineers have derived formulas or charts that give you NT if you know NTU-C and the flow arrangement.
So if you know the exchanger type, size, which gives you A's, the U value, the fluid properties to get Cmin and Cmax, you can calculate NTU and C, find the effectiveness A, and then calculate the actual heat transfer rate. No iteration needed.
Precisely. It's much more direct for predicting performance.
Is there a key design insight from this NTU stuff?
Yes, definitely. If you plot effectiveness versus NTU for a given capacity ratio C, you find something interesting. The effectiveness increases quite rapidly as NTU goes from 0 up to about, say, 1.5 or 2. But then the curve starts to flatten out. Increasing NTU further gives you diminishing returns.
Meaning making the heat exchanger much bigger doesn't help much beyond a certain point.
Exactly. For NTU values larger than maybe 3, you have to make the heat exchanger significantly larger, increase A's, to get only a tiny little increase in effectiveness. So here's the crucial design insight. Using a heat exchanger with an NTU much greater than 3 is generally not economically justifiable. The extra cost of the larger unit just doesn't pay off in terms of significantly improved performance.
That's a really practical takeaway. And does flow arrangement matter for effectiveness?
It does. For any given NTU and capacity ratio C, a counterflow heat exchanger generally has the highest effectiveness compared to other arrangements like parallel flow or crossflow. Another reason counterflow is often preferred.
Okay. What about those phase change cases like condensers or boilers?
That's a special case where the Effectiveness-NTU method simplifies nicely. When a fluid is condensing or boiling, its temperature stays constant during the phase change. This effectively means its heat capacity rate, C, is infinite because it can absorb or release heat without changing temperature. So the capacity ratio, C, Siemens Cmax becomes 0.
C goes to 0.
Right, C0. And when C0, the formulas for effectiveness simplify, and interestingly, the effectiveness becomes the same regardless of the heat exchanger type, for 00 AAO AAHE A-NTU.
Wow. Okay, so LMTD for sizing when temps are known, Effectiveness-NTU for predicting performance when size is known. Two key tools.
Exactly. They complement each other depending on the problem you're trying to solve.
Right. Beyond these calculations, though, choosing the right heat exchanger in the real world must involve balancing a lot of practical factors, right? It's not just math.
Oh, absolutely. The calculations tell you if it can do the job, but selecting the best one involves trade-offs. A tiny design choice can ripple through performance and cost.
So what are the big things engineers consider? Obviously, the heat transfer rate itself is number one.
Fundamentally, yes. It must meet the required heat transfer duty specified for the application. That's non-negotiable.
And cost, I imagine, is always huge.
Always. And it's not just the initial purchase price. You have to think about the ongoing operating costs, especially pumping power and maintenance costs over the lifetime of the unit. Sometimes an off-the-shelf standard unit might have a lower purchase price, even if it's not perfectly optimized just due to mass production.
Pumping power. You mentioned that with PCHEs having high pressure drops. That's a big operating cost.
It can be a very significant one, especially for large industrial units moving a lot of fluid, and that brings up a crucial trade-off.
Which is?
Well, generally, if you want to minimize the pressure drop and therefore the pumping power cost, you need lower fluid velocities. But lower velocities usually mean lower heat transfer coefficients, lower U. To compensate for the lower U and still get the required heat transfer, you need a larger surface area, ACE-S, which means a bigger, more expensive heat exchanger up front.
So save on operating cost, pay more initially, or save on initial cost, pay more to run it.
That's the classic trade-off. As a rough rule of thumb, doubling the mass flow rate through an exchanger might cut the required surface area, and thus initial cost, roughly in half. But it could increase the required pumping power by a factor of maybe 8, because pressure drop often scales with velocity squared, and power scales with pressure drop times flow rate.
Wow, a factor of 8, that's huge. So finding the sweet spot is key. Are there typical velocities engineers aim for?
There are typical ranges, yeah. For liquids, maybe somewhere between 0.7 and 7 meters per second. For gases, because they're less dense, velocities are usually higher, maybe 3 to 30 meters per second. But it depends heavily on the specific application and that cost trade-off.
Okay. What else? Size and weight seem obvious, especially for certain applications.
Definitely critical in automotive, aerospace, anywhere space or weight is at a premium. That's where compact exchangers really come into their own.
The type of exchanger also matters, presumably based on the fluids.
Absolutely. Are you exchanging heat between two liquids? Liquid and a gas. Gas and a gas. Are there phase changes involved? Is one fluid much more viscous or prone to fouling? All these influence the choice. For standard liquid-to-liquid duties without extreme constraints, shell and tube or plate and frame are often the default choices.
And the materials you build it from must be crucial, too.
Vital. The materials have to withstand the operating temperatures and pressures, of course, but they also need to be compatible with the fluids you don't want corrosion eating away at your expensive exchanger.
Are there limits where materials become a really big issue?
Yes, thermal and structural stress become major design drivers at very high pressures, say above 70 atmospheres or high temperatures, above maybe 550 degrees Celsius. Also, even moderate temperature differences, say 50 degrees C, between the tubes and the shell in a shell and tube exchanger can cause problems due to differential thermal expansion. The tubes want to expand more or less than the shell, creating stress. You might need expansion joints or specific designs to handle that.
Well, lots to think about.
Yeah.
Any other factors?
Sure. Things like leak tightness are critical if you're handling toxic or very expensive fluids. Ease of servicing and maintenance, can you clean it easily if it fouls? Safety and reliability are always paramount. And sometimes, like for HVAC systems in buildings, low noise operation is important too.
It's a complex decision matrix.
It really is. Balancing all these factors, performance, cost, operation, materials, safety, is what heat exchanger design is all about.
Can you give a quick example of how choosing the right exchanger makes a real-world difference, maybe in terms of cost savings?
Oh, definitely. Consider, say, a dairy plant. They often have a lot of hot wastewater from cleaning processes. Just draining that hot water is wasting energy.
Right.
By installing a relatively simple heat exchanger, maybe a plate and frame type, to recover heat from that hot drain water and use it to preheat the incoming cold, fresh water, they can save a lot on their fuel bills for heating.
How much are we talking?
While studies have shown that recovering even just 75% of the available heat from drain water in a typical dairy could save something like over $20,000 per year in natural gas costs. The heat exchanger might pay for itself in just a year or two. That's a huge impact.
Wow. That really puts it in perspective. Okay, now, for something completely different but related, you hinted earlier, heat exchangers in the human body.
Ah, yes. This is where it gets truly fascinating, I think. Because did you know you're walking around with one of the most sophisticated countercurrent heat exchangers ever designed?
I am. Where?
Your cardiovascular system, specifically the way your arteries and veins are arranged, especially in your limbs. It's crucial for thermoregulation, keeping your body temperature stable.
How does that work? Arteries and veins, they run next to each other.
Very often, yes. Especially deeper within the limbs. Arteries carrying warm blood from your core down towards your hands or feet are often intricately paired, running right alongside veins, carrying cooler blood back up from those extremities towards the core.
Okay. So, warm blood going out, cool blood coming back, right next to each other. What happens?
Countercurrent heat exchange. Think about when you're in a cold environment. That warm arterial blood flowing down your arm towards your cold hand starts transferring its heat to the cooler venous blood flowing back up right beside it.
So the blood going out gets cooled down a bit before it even reaches the hand.
Exactly. It pre-cools the arterial blood. This means there's less of a temperature difference between the blood reaching your hand and the cold environment, so you lose less heat overall from your hand to the surroundings.
That's clever. It's like minimizing the heat loss at the source.
Precisely. But there's a second benefit, equally important.
Which is?
That heat transferred from the artery doesn't just disappear, it warms up the returning venous blood.
Oh. So the cold blood coming back from the hand gets pre-warmed before it gets back to your core.
Yes. It helps prevent that cold blood from chilling your core body temperature too much. It's a brilliant system for conserving core heat in cold conditions.
Wow. It's like your body is recycling heat within the limb itself, reducing the driving force for heat loss to the cold air. That's amazing.
It really is. And if we connect this to the bigger picture, research looking into this has shown that this countercurrent arrangement effectively enhances the thermal conductivity of the surrounding tissues.
Enhances conductivity. How?
By facilitating this rapid heat exchange between vessels, it makes the whole limb region better at managing heat distribution. The effect is noticeable, maybe a 5% enhancement for the tiniest vessels, but potentially up to 70% for larger vessels closer to the skin. It just highlights how remarkably efficient this natural design is.
So it's a measurable effect. Do we know, like, the U value for blood vessels?
Well, simplified models have been developed. One study looking at paired vessels estimated an overall heat transfer coefficient of around 117 watts per square meter Kelvin. It shows how temperatures can change quite significantly along the length of these paired vessels as heat is exchanged, allowing the body to carefully regulate heat flow to the extremities.
Incredible. And this isn't just about keeping hands and feet from getting too cold.
No, this mechanism plays other critical roles too. A really fascinating example is selective brain cooling, which has been observed in animals like sheep.
Cooling the brain.
Yes. They have a network of blood vessels, a carotid rete, where warm arterial blood going to the brain passes through a pool of cooler venous blood draining from the nasal passages. This acts as a countercurrent heat exchanger to cool the arterial blood slightly before it reaches the brain.
Why would they need that?
It helps protect the brain from overheating during exercise or heat stress. And remarkably, in dehydrated animals, this mechanism can also significantly reduce water loss from panting, saving perhaps liters of water per day.
That's absolutely incredible. Nature's engineering is just wow.
Isn't it, though?
So wrapping this up, from these massive industrial giants that make our modern world run efficiently, processing chemicals, generating power, all the way down to the intricate, totally hidden systems working inside our own bodies right now to keep us alive and comfortable, heat exchangers are just truly a foundational technology.
They really are. They're a perfect testament to how these fundamental principles of heat transfer, convection, conduction, radiation, these temperature differences, how they underpin just so much of the world around us, both built and natural.
So what does this all mean for you listening?
Well, maybe the next time you feel that cool breeze from your air conditioner, or you sip a warm drink, or even just feel the warmth in your hands on a cold day, take a second to consider that unseen dance of energy that's happening, the deliberate transfer of heat, perhaps even within yourself.
Yeah.
And it really makes you think, doesn't it? This raises an important question. How else might nature have optimized heat transfer in ways we're maybe still discovering? What else could we learn from its designs? There's probably so much more out there.
That's a great thought to leave with. Take a moment. Think about other systems in your daily life, big or small, natural or man-made, that might secretly be operating as heat exchangers, impacting efficiency, comfort, maybe even survival. We hope this deep dive has given you a whole new appreciation for something as fundamental, yet as sophisticated, as the simple act of transferring heat. Thanks for joining us.